Hello kids, I want to give you some insight into section 3.4, which was derivatives of inverse trig functions. But I know that some of you are questioning this whole domain thing and what he's talking about with that. So let me go back to pre-calc for a minute and see if we can maybe clear up some of the thoughts about what the heck is he talking about with the domain and restricting domains and such. So here's the story. You've got an inverse function. Right, here you go. I'm going to start with our normal happy parabola, and he's a good function for us to start out with, because in order for something to have an inverse, it needs to pass the horizontal line test and the vertical line test. So look at Mr. Happy Parabola. Does he do that? He's cool with the vertical line test. He's a function. But as soon as you start a horizontal line test, he's going to fail it. So here's what tends to happen in order for it to have an inverse back in the days of pre-calc. You would have to only look at part of the graph where it would then pass the horizontal line test and the vertical line test. So think about what that would look like. You want the largest possible part of the graph that would pass the horizontal line test and the vertical line test. So I'm going positive here. So I would pick this part right here, right? If I look at that part of my x squared graph, then I know that it passes the horizontal line test and I know it passes the vertical line test. And so what that requires me to do is restrict the domain. I'm only looking at the part of the graph that's greater than or equal to 0. Could I have picked the left-hand side of this and then just said x is less than or equal to 0? And you can say, yep, I could have. I just chose to stay positive. So you're restricting the domain so that it then fits the criteria of passing the horizontal line test and the vertical line test. Now let's look at the trig graphs, because that's really where we were with this particular section. You're looking at inverse trig functions. Here's a sine graph. Now you always want to stay around 0, around the origin. So you're going to try to pick that, look at the largest possible piece around the origin, close to the origin, including the origin maybe, that would be able to pass the horizontal line test and the vertical line test. So let's start over here. This would fail. I've got a horizontal line test that isn't happening. So it can't be between negative pi and 0. That's not going to work. But let's say if I started here at negative pi over 2. If I look at just this section, from negative pi over 2 to 0, that's fine. That passes everything. That's happy. That's a vertical line test pass and a horizontal line test pass. If I keep going, look at, I can even go further. I want the largest possible piece that'll pass the horizontal line test and the vertical line test. If I keep going, oh, no longer works. All right, so I can go from negative pi over 2 to positive pi over 2. Right? And that part right there is going to pass the vertical line test and the horizontal line test. So now let's think about what quadrants we're in, because that's going to be helpful to us when we go to look at the table that we've made of trig values. So if I look at this, if I'm between negative pi over 2 and 0, think about your unit circle. If I'm between negative pi over 2 and 0, I'm in quadrant 4. And if I'm between 0 and pi over 2, I'm in quadrant 1. So the sine, I should put it over here. I can't fit it yet. If I have y equals the inverse sine of x, the only places I'm going to have values for that are in quadrant 1 and quadrant 4, because that's where the inverse would lie. Okay? If I go to the cosine graph, if I look at just this piece part in here, that's not, oh, you gotta see my picture. If you're gonna look at this part here, you're gonna fail the horizontal line test, right? So that's not gonna work. If I come to 0 and start at 0 and do the same type of thing as what I just did with sine, it is passing, everybody's passing, HLT, VLT, HLT, VLT, until I get to here. That's the biggest piece of the cosine graph that I can put together that's going to pass the vertical line test and the horizontal line test. So this time, if I'm looking at which quadrants I'm in, between 0 and pi over 2, I'm in quadrant 1. And if I'm between pi over 2 and pi, I'm in quadrant 2. And that would be for my inverse cosine function. Okay. That's restricting the domain so that I get just a one-to-one function. Now, tangent graph is the tangent graph, right? It's these continual curves that you've got going on, kind of look like cubic functions almost. But if I look at this guy, if I look at the graph of just the one section there that's between negative pi over 2 and positive pi over 2, that whole section of the graph passes. So that one was easy peasy. So this one is going to be, let's think about the quadrants though. If I'm looking at the inverse tangent graph between negative pi over 2 and 0, well, that's quadrant 4. And between 0 and pi over 2, that's quadrant 1. And they would be the values that you're looking for when you're at the tangent to the negative 1 for your function. Okay, I know that some of you had questions about what the heck is this whole restricting the domain talking about, and that's what the story is. All right, I'm going to try to quickly explain our notes a little bit, clear them up a little bit. Hopefully you had time to put these on your card. Remember that if it's signed to the negative 1, that negative 1 notation is the same thing as if it were called the arc sign. They mean the same thing. So sometimes they're going to tell you arc sign, sometimes they're going to tell you sign to the negative 1, but either way they're looking for the inverse of the sine function. So you've got all of your rules, and he kind of went through and gave you some directions on how to remember which ones are positive and which ones are negative. The one thing I don't think he did do was on the actual rule part here, he forgot to add in that you really need to also take the derivative of whatever x is. So I put it on mine. You might want to put it on your cards if you didn't already. But you've got the actual value for what the inverse sine is, and then you want to take the derivative of whatever x is. And you can see that in the problems. Like, so see, in number 1, you want the inverse sine of 3x. So you're going to put 1 over the square root of 1 minus 3x squared, but then you need to multiply by the derivative of 3x, which is 3. And so that's going to come into play to give you the answer. So I don't believe he put these x primes in his notations, but you might want to add them to your card so you don't forget that you're kind of chain ruling it, right? You're taking that inverse, whatever the inverse rule is, and then using the chain rule on it. These are just plugging in. This was a little confusing. You have to decide sometimes if they're positive or negative. If I have a 9x squared, there's no way I can put anything into that that's going to come out anything other than positive. So I have a numerator that's always going to be positive. Check out the denominator. My denominator in x to the 6th, that's always going to be positive. This could be negative, an x cubed, right, an odd power. Except the problem is that then I'm taking absolute value of that. So I have a always positive over an always positive, and so therefore my answer is going to be always positive, and I'm reducing. 9x squared, 3x cubed gives me just an x with the 3 on top, and then you've got your root. So it's really just the outside pieces that you're reducing when you reduce these. For number 5, this one, 4x, I could put in a negative value for x and it would be negative. I could put in a positive value for x and it would be positive. So this one could be positive or could be negative. Your denominator is always positive. So as you're looking at this, it could be negative, so you're going to take away the absolute value. So you don't want the absolute value in there when you reduce it, because you could actually have a negative value. A little weird, but true. I can tell you that this is not a hot topic in what you're going to see on the AP test. So if it's not sitting with you, don't worry about it. All right, this is all what I just was talking about with the graphs. Remember, we just talked about this a few minutes ago. The inverse sine graph is in quadrants 1 and 4. That means when you go to your chart, the chart you have with all the trig values on there, you're only looking at values that are in the first quadrant or the fourth quadrant. You're not looking at the entire chart. You're skipping over anybody that's in quadrant 2 or 3. And I'll talk about that in a minute. For cosine, you're only in quadrants 1 and 2 from that chart. and for tangent, you're only in quadrants 1 and 4 for that chart. And they talk about the domain restrictions and the range restrictions and yada yada. But we just talked about that in the picture. All right, last little bit. I don't know if you remember much about inverse trig functions, but one of the things is that they're inverses, right? So you're switching things. So if I had the sine of theta is 3/2, the square root of 3 over 2. And I want to know what angle that happens at. You would go to your unit circle, or go to your chart, right? And you're looking for where, and you're only in, remember which quadrants for sine, 1 and 4. In the first quadrant or in the fourth quadrant, where is the square root of 3 over 2? What's the angle that goes with it? And the angle that goes with it is pi over 3. This one is asking you, plug a -2 in. -2 over 4 is a -1/2. In the first or second quadrants, this is cosine, where do you have an angle that the cosine is a -1/2? That's quadrants 1 and 2. You end up at 2 pi over 3. That whole chart's going to be very handy for you in this particular section. Same thing kind of goes here. I want to know where is the tangent 1 over the square root of 3. Well, tangent has to be in first or fourth quadrants, so you're looking in those two locations. 1 over the square root of 3 is the same thing as the square root of 3 over 3, and so you want to know where that happens, and that happens at pi over 6. And they were all of the example problems. Now the practice problems, they're pretty standard. You're just plugging in whatever this is, and then don't forget to multiply by its derivative, and then setting it up and simplifying it out. Number 5 caught me. I don't know if it caught you, but it's not an inverse. It's just a regular old cosecant. So be careful of that. All the rest of these are either arc cosines or inverse cotangents or whatever they are. If they can reduce, you want to reduce them. Number 9 was one of those. Number 9, you've got from the rule and then times the 6x to the 5th. I can actually reduce these. So 6x to the 5th over an x to the 6th is just an x on the bottom, but it can be negative. So that means you remove the absolute value signs as you reduce it. And otherwise, that's it. That's the deal. So that one's the only one that's kind of goofy. For 11 and 12, you were looking for a point. So if x is the square root of 2 over 2, where does that happen for sine? And that happens at pi over 4. So you go to your chart, you figure out what the coordinate is. So now you get a point, and they want a tangent line. So you're going to go through and you're going to figure out what the slope is, what the derivative is. And then you can put the point and the slope together into your equation for the tangent line, and there you go. So not too bad. It's just, these are kind of, nobody likes fractions and ain't nobody likes square roots. So they're a little bit ugly, but they're not undoable. They're okay. You can handle it. The last little bit here, 13, 14, 15, 16 are all the same thing. Let's see. I have to figure out, I'm looking at 13 particularly for this first one. I've got an x value of the square root of 3 over 3. Go to your chart, you get pi over 4 is your value that would happen at. And then find the value of your slope, which comes out to be a square root of 3. Now up at the top is where I kind of boxed in what my tangent then would be. So here you got your point, you got your slope, you can plug it together, and that's your deals for 13, 14, 15, and 16. And we'll talk answers to the test preps when we gather again together. So there's kind of a quickened version of section 3-4. I hope that the explanation about restricting the domain is helpful. And I'm also hopeful to see you in class on Thursday. Stay well, and I'll talk to you soon. Bye.